The Raychaudhuri equation is the cornerstone of modern cosmology and gravitational physics. This equation, formulated by Indian physicist Amalkumarraychaudhuri in 1955, has played a pivotal role in shaping our understanding of the cosmos. But why is this equation so significant and important? Its implications extend far beyond mere mathematical formalism. The Raychaudhuri equation has been instrumental in elucidating the nature of singularities in spacetime, particularly in the context of black holes. In fact, it served as a crucial mathematical tool in the development of the Penrose Hawking singularity theorem. Today we are going to look into this equation, which lies at the heart of all gravitational singularities and also pushes us to the edge of the most dominant physical theories of our time, Einstein's General Theory of Relativity. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to this fresh new video on what is called the Raychaudhuri equation. First, we would look into what is the equation all about, a general idea about Amalkumarraychaudhuri, who is popularly known as AKR. Now, as you see right in the screen, this is a very, I would say, a very common photograph of AKR. Born in 1923, is an Indian physicist known for his research in general relativity and cosmology. His most significant contribution is the eponymous Raychaudhuri equation, and this is a very fundamental equation, as we will explore further in Einstein's General Theory of Relativity. And we should remember that this is the equation, the most important equation, which helped Roger Penrose and Stephen Hawking to prove their very famous Penrose Hawking singularity theorem. And the most important thing that we should also understand is that the Raychaudhuri equation is not only restricted in the scope of general theory of relativity, but in every sphere of geometry, or I would say every sphere where there is a flow or where there are vector flows, we have what is called a Raychaudhuri equation. Now, when I say that it is not restricted to the scope of general relativity, does it mean that it goes beyond the other spheres of physics? Exactly so. But indeed, Raychaudhuri or AKR developed the Raychaudhuri equation keeping in mind Einstein's general theory of relativity, and most importantly, the Raychaudhuri equation developed, AKR actually formed the equation based out of Einstein's field equations, as we will see. So this is basically a general idea of what and why it is so important in our understanding of singularity. Let us look into what this equation first looks like and what are the important features, and then we will further develop certain very important and very interesting features. Now, the Raychaudhuri equation, as you can see on the screen, might look like this or this or this. Now, why I'm showing you the three different, or maybe there are further, because all of these are basically the same. All of these equations are basically the same Raychaudhuri equation, but these equations have something very common in all of them, and we are going to explore on that. But there are maybe another one or two different types of Raychaudhuri equations. The reason is that depending upon the dust, depending upon the expansion of the universe, the parameters and the values of the Raychaudhuri equation goes on changing. Now, what is important is that there are certain common things. What are those? Let us look into the next part of our video. So here you will see that there is something which is called a sigma squared, which is very common in all those three equations. Remember, these are different ways of writing the same Raychaudhuri equation, but they are sometimes, confined, or I would say they are reduced with certain, Greek alphabets to make things easy. So these sigma actually denotes one very important thing, which is called shear. Now, when I tell shear, it is not only shear, it is shear squared. So this gives a combined measure of how much deformation is happening in different directions. Okay, let me first explain what do I mean by deformation in this part. So here is our universe, for example, and this has got an uniform expansion. So the universe is expanding uniformly in every direction. Then we have a uniform contraction. That means it is contracting uniformly and it is further and further and further contracting. And when it goes for a shear, there's a distortion or deformation, it looks something like an ellipsoid, tentatively. So what I am trying to say is that unlike a uniform expansion or a uniform contraction, where all observer may move away or towards each other equally, shear actually describes where the expansion and contraction rates differ in different directions. That means it is not uniform. Unlike the uniform expansion contraction, there is something which is not uniform, and this actually describes the rates, how much the rates differ in different directions, which is the measure of the shear. Now, why I am measuring shear? Obviously, these things will become important. So, this you can see that in every form of Raychaudhuri equation, there is one sigma, which is the shear. Next, what we find is that all of those equations have got a value of omega. Now, in the second equation, this is noted as xi, because I have not showed the expanded form, but this xi is actually a contracted form of the rotation, which is called the velocity vorticity. But anyway, you can understand this is also rotation. So all this equation again have something which is very common, which is called rotation. Now, why rotation? Because the rotation term is very important and central in Raychaudhuri equation. Now, the rotation term in the Raychaudhuri equation represents the collective rotation of a congruence of time-like geodesics. Now, don't worry, I'm going to explain you what is a congruence of time-like geodesics. But let us understand that the rotation term tells you how much they rotate as a whole relative to some fixed background. That means fixed background of space-time. So why rotation is important? Because analyzing rotation alongside expansion, which I showed you just now, and shear, which I also showed you, gives a complete picture of how the observers move and deform within space-time. Now, when we talk of observers here, what do I mean? I will just show you. This is actually the geodesic movement, which we called in terms of observer. So the rotation is very important and it plays a pivotal role in singularity theorems, though its impact is often weaker because under specific conditions the behavior of rotation can contribute to the prediction of singularities. So and also this is called vorticity, and we will see later that this is actually in a tensorial form, which is called a vorticity tensor. So two things we have just seen which is very common in Raychaudhuri equation. One is the shear and one is the rotation. Now if you move further, then we see that there is a r and a r double dot. That means it is a second order differential, and there is something like this, and this is actually which is called the acceleration field. Now, why we are mentioning this acceleration vector field, I will let you know in soon. But just remember that the original paper of AKR, which was published in the Physical Review 1955, did not introduce the acceleration term because AKR was only interested in the geodesics, and this is how actually the original Raychaudhuri equation looks like as it is published in the Physical Review. So more or less you can see there is something which is acceleration, and we will deal with acceleration obviously because that leads to the contraction of the universe, formation of singularity, etc. So more or less this is how the Raychaudhuri equation looks like. The two most important features are the shear, which creates a distortion or a deformation, and there is a rotation, and this rotation is denoted by the omega, and the shear is denoted by the sigma sign. Now, before going further to understand the Raychaudhuri equation, we need to understand certain mathematical terms, or I would say certain concepts. And until we understand those concepts, the Raychaudhuri equation, because I would be using those terms later, it won't be easy. So let us look into some of the fundamental concepts, which is very fundamental not only to Raychaudhuri equation but into general gravitational cosmology also, coming up in the next part of the video. So first we would look into what is called congruence of time-like geodesics. Now, what is congruence of time-like geodesics? First, let us understand that what it actually is. So, in general relativity, a congruence of time-like geodesics actually refers to a collection or a family of world lines. That means a kind of a trajectory, you can say, but it is not one, but it's a collection or a family in space-time that follows certain specific conditions. I will come to what the conditions or those conditions actually those geodesics follow. But what is very important is that, remember, studying Raychaudhuri equation is the analysis of defined families of trajectories as opposed to a single trajectory. So we are trying to understand and analyze the behavior of certain, I would say, family of trajectories. Now, why family of trajectories? Because once we understand the family of trajectories, we can easily predict the behavior and what those geodesics will look like. Now, I was talking about that the congruence of timelike geodesics is a collection which follows certain specific conditions. First condition is what? It is time-like. I hope this is absolutely school level physics. I don't need to explain what is time-like, but just to make you an kind of an understanding, this is what is time-like. So each world line represents the path of a freely falling, non-accelerating observer. In mathematical terms, we can say the tangent vector to each world line points in a direction with positive time component and a negative squared magnitude relative to whatever the metric that we are selecting. So this figure actually shows something which is called time-like. So in my previous video, I have explained what is a time-like, space-like, and light-like in that Minkowski's contribution to make up things. So this is what we call time-like. Now, what is basically a geodesic? We all know that it is the straightest possible path allowed by the curvature of space-time. Now, there is a new term which we are including here. Note that this is called congruence. Okay. In general, what do we mean by congruence? Congruence congruence in terms of obviously general relativity means exactly one geodesic is passing through each point in a specific region of space-time. So there is only one geodesic is passing and there is no, I would say, intersection. So what does it ensure? It ensures a consistent and organized distribution of observers, unlike randomly or scattered individual lines. Now let me show in a diagram. So these are actually congruence. This line, the blue lines which you can see on the right hand side. And so in a very simple term, we can say congruence means a family of non-intersecting geodesics. Now you might question me, what will happen if the geodesics intersect just like this in the red dot? This would lead to singularity. And that would cancel out a lot of possibilities which we will later look it up. So first thing is that the congruence of timeline geodesics is the central area of Raychaudhuri equation, because Raychaudhuri equation deals with the behavior of this congruence of timeline geodesics. That means geodesics that would pass through each point in a specific region of space-time, they are non-intersecting geodesics. Now, when we talk of geodesic, there are certain important things which also comes. I mean to say, we cannot ignore those important points. First, which is called a flow. Now, you can imagine this as a flux. You can imagine as a flow of magnetic lines, electric lines. That is totally dependent on you. So, the flows are generated by a vector field. Now you see, I just spoke right before starting this video that Raychaudhuri equation is so fundamental that it goes beyond the scope of general relativity. Anywhere there is a vector field, anywhere there is a geometry, there is a Raychaudhuri equation. And the reason we are coming slowly to that. Number one, flows are generated by a vector field. Number two, a flow is a congruence of such curves, because we are dealing with geodesics. So obviously the full flow is a congruence of such curves. On the left hand side, I've just given a schematic diagram of a flow. Mind it is not the actual geodesic. It can be anything flowing through a bottle, electricity, magnetism over a specified area. Now this is important. When we are studying Raychaudhuri equation, we do not ask how the flow is generated. Rather, what we do is that we determine the kinematic characteristics of such flows. That means we don't say how the flow is generated. What is the reason? Rather, we determine the kinematic. That means how the characteristics of such flows actually happens. That means we can say that the evolution equation, that means Raychaudhuri equation is basically an evolution equation of the quantities that characterize the flow in a given background space-time are the Raychaudhuri equations. I repeat, flows are generated by vector field. We do not ask how the flow is generated. Rather, we try to determine the kinematic characteristics of such flows. And Raychaudhuri equation, which is essentially evolution equation which moves along the flow of the quantities that characterize the flow in a given background spacetime, are the Raychaudhuri equation. Those set of equations that characterize the flow in a given background of space-time are basically called Raychaudhuri equations. So this is what the flow and the congruence of timelike geodesics are related. But it is also worthwhile to note this one. In general relativity, if we talk a little bit technically, we call a flow, or I would say congruence, is a set of integral curves, because we have to take an integral, we are taking a family of those curves, right, of a vector field, obviously the 4-dimensional Lorentzian manifold, which is interpreted physically as a model of space-time. Now congruences generated by nowhere, I would say vanishing time-like, null or space-like vector fields are called time-like, null-like and space-like and so on. This I hope you understand. Now a congruence is called a geodesic congruence. When it will be called a geodesic congruence? When it takes a tangent vector field, say for example x, and it should have a vanishing covariant derivative. Now right now this is not the right place to explain what is a covariant derivative, but those who know, you can skip that, but those who do not know, understand that the general partial derivative won't take place in a kind of a manifold, because it is very much curved, it makes weird kind of predictions, so we have to do a covariant derivative. And the covariant derivative is what? It is actually a correction term, which I can explain later using the Christoffel symbols, etc. And this is used by the nabla sign. So what this covariant derivative denote is this, very important. This means that the observers are following free falling trajectories under influence of gravity, not experiencing any additional force or accelerations. This is important because Raychaudhuri equation deals with the family of congruence of time-like geodesics, so it should not experience any other external forces, but it should be free falling trajectories and under the influence of gravity. So this is what is called the congruence of timeline geodesics, which is going to be very central in our understanding of Raychaudhuri equation. So I thought to give you the basic idea. The second concept which comes is called the formation of a caustic. Now if you look into the caustic in the spectroscopy term, it means burnt. I mean, it is something which burns actually. But in terms of general relativity, as you can see here, given a space-filling set of straight lines, for example, a caustic occurs when their intensity diverges to infinity. So on the left-hand side the figure, you can see all those lines are diverging to infinity. So this is actually the pin part, the top, absolutely the apex of this pyramid is actually causing the caustic. So what in terms of general relativity, of what we can say, that caustic formation refers to the phenomena where light rays or other geodesics converge and become infinitely focused. Now this is very important in terms of general relativity and Raychaudhuri equation, because this caustic formation will help us to determine the size or determine the characteristics of a black hole and the trapped surfaces, etc. So here you can see another diagram which I have given. This is also a caustic and the generators are crossing. So this is on the Minkowski space. So we can say that this caustic actually, this creates regions with dramatically increased intensity or density, similar to how light rays can focus under magnifying glass. So when you get a kind of a light rays gleaming down the magnifying glass, so it actually focuses at one point. So that is why this is very important. We will soon see the importance of caustic in terms of geodesics, etc. Now there can be two types of caustic. One is called a null caustic, which is focusing of light rays on null geodesics, which leads to gravitational lensing, which you already know. Our JWST telescope is smart enough to show a lot of gravitational lensing, and NASA is constantly producing those pictures. Another is called focusing singularities, that is caustic formation can lead to singularities, and you can understand the very reason. The next thing is called time-like caustic. Now time-like caustic is focusing of time-like geodesics representing trajectories of objects with mass. Obviously this has got time-like, so it has to have a mass. And this leads to one which is called a collision dynamics. Why? Because black hole mergers, caustics can form, leading to highly energetic collisions of particle creation. And it can lead to future singularities, because caustics might play a role in exhibiting what is called the future singularity. So these are the two types of caustics which are being formed. Now when we talk of general relativity and the convergence, this is a kind of a diagram which is, you can, so caustics will develop in a congruence if convergence occurs, and this holds for congruence in Minkowski spacetime also and many other singularity free spacetimes. Now you see this caustic is also embedded in the Raychaudhuri equation. If I take these two equations, I'm going to say I'm just taking random so that you understand that both of them are the same. This theta term, d theta and a theta dot. So if the initial value, remember at theta 0 is negative, this means that our geodesic must converge in a caustic. And this is happening right on the left hand side figure. So if the initial value of theta 0 is negative, they will converge and they will form a caustic. Here is another diagram which shows two caustics formed by the space-like lines, the lower end and the upper end. These are again which are showing two caustics. Now I just explained you that caustics play an important role in the formation of black holes, etc. Now let me show a very simple diagram which will help you with a nice little animation to help you understand. Here you see when a black hole forms by a gravitational collapse, a caustic is formed at one point by the set of light-like world lines. Obviously, it's a form of a black hole which is formed by a light-like world lines that enter the event horizon from the outside universe at the moment when the horizon is formed. Now pay attention on the left hand side of your screen. This is a light-like, right? It is moving up, and this is the black hole which is formed. Step 2. Now what I am doing, these are the lines which are forming the caustic, and this green line is the event horizon. Now you see what happens if a light ray is emitted from the caustic point, it remains on the event horizon forever, as do all rays emitted at the event horizon in the outward direction at later times. It is never going to cross the event horizon. And pay attention on the left hand side diagram. Here it is the light ray is emitting, and here it stops just at the edge of the event horizon. So this is another very important and interesting feature of caustic. So the event horizon is the same set of events as the union of the light-like world lines. Obviously, all the light-like world lines which are going and forming that caustic, the event horizon is the same set of events as you can join all the light-like world lines that enter the horizon of the caustic. So caustic formation is again a very integral part of a Raychaudhuri equation. The next and perhaps the most important thing is the expansion, rotation and shear. And I'm going to explain why this plays a very, very important role in our understanding of Raychaudhuri equation. Now here the lines are moving, right? So, and you see these nice universe and galaxies, these are all rotating and come to halt. So this is what? This is an expanding universe. And let us imagine that the world lines could represent galaxies, stars, nebulae, whatever. They are getting further and further apart because of the cosmological expansion which resulted from the Big Bang. And as we know that our Edwin Hubble tells that the galaxies are moving away from Earth at speeds proportional to the distance, and we can measure that by a Hubble's constant. This is one part which is called the expanding universe. Now you see this is the rotating universe. So the lines are rotating. This is called a rotating universe, and you can imagine those satellites and other things, or anything these are orbiting, so they're rotating. So these world lines could represent a constellation of orbiting satellites or any other things that are going around in a rotating laboratory. So this is the expanding, this is the rotating, and this is what is called, the most important is the shear. So shear refers to a specific aspect of the deformation experienced by a bundle of geodesics as moved through the curved space-time. Now, whenever I am talking of bundle of geodesics, you should remember I am talking of a family of what we called just few moments ago that a congruence of timelike geodesics, a family of geodesics which are moving. Now there are few important points in shear which we need to understand. Number one, how the shape of the bundle of geodesics change as they move. Shear helps us to understand. It also measures the non-uniformity of the expansion. Obviously, the expansion is not uniform. Otherwise, how it would result into shear. Capturing how the relative separation between different geodesics with the bundle change. How the relative geodesics, the family of geodesics, are changing. Shear plays a very important role in the caustic formation. And while the expansion term tells us if the bundle is converging or diverging, shear also tells us how the convergence occurs. I'm not going to explain how the convergence occurs because it will take another different kind of a topic where I have to explain the different types of singularity, but this actually tells you how the convergence occurs. The next fundamental concept in understanding Raychaudhuri equation is called what is homogeneity and isotropy. And these are things which sometimes I have seen that students, they get confused. So more or less they are the same. I will just explain to you. So homogeneity means that the universe looks the same at every point in space on an average. That means I am saying that there are no special or there are no preferred locations. And we can say mathematically, although I have not used any mathematical equation as such, that the energy density, pressure and temperature are constant throughout the universe at any given cosmic time. So the physical observables which we see, the energy, density, pressure, they are constant throughout the universe at any given cosmic time. What is isotropy? Now isotropy is also more or less the same. So means the universe looks the same in all directions on average. So here comes the concept of direction. And there are no privileged locations, just like homogeneity. And mathematically, you can say the isotropy is expressed by stating that physical observables, just like what we did in homogeneity, do not depend on the direction in which they are measured. I'll give you an example, very unique example, you will understand. So isotropy means that the entire physical observables do not depend on whatever the direction that we are measuring. And homogeneity is the same physical observables, but they are constant, average constant throughout the universe. So isotropy implies that the universe appears the same when observed from any vantage point. Now look at this deflated balloon, right? So it has got few points, the red balloon which has got white dotted points, and you can imagine those as galaxies. Now what I do is that I inflate that balloon and I use these marks. You can see that these marks or the yellow lines are showing the distance. That means it is another quite nice example to explain homogeneity, that even if the balloon is inflating or the universe is expanding, although there are the distances between those white dots are measured with a distance, but yet overall it remains the same. So this is very important. Even though galaxies are moving away due to expansion, the large scale distribution of matter stays approximately homogeneous and isotropic. And this is very important. I will come to AKR's own statement. So this is what is called. You can also think it as a nice pizza, right? This is a nice pizza right on your screen. And you can see that all this pizza is got evenly distributed toppings, all the pepperoni, olives, chicken, mushroom, etc. And this represents homogeneity. That means everywhere on the pizza, you have a similar mix of ingredients. Now you rotate the pizza, this one, this blue line. Now the question I would ask is that when you rotate the pizza, does the distribution of the toppings changes? No. Why? Because it is isotropic and there is no preferred direction of the toppings. So this is very important. And you should remember one thing, that homogeneity and isotropy, although we are making a difference, are just mere approximations. Because on smaller scales, what do we observe? We observe structures like galaxies, clusters and voids which deviate from perfect uniformity. So both these concepts are they refer to large scales, not to the small scales. So typically hundreds of millions of light years or more. So on smaller scale, that is the observable universe, local variations and inhomogeneities very much exist. And here comes the final thing. Raychaudhuri equation actually does not include homogeneity and isotropy. We will soon see and what is the result of that not inclusion of homogeneity and isotropy. The next important concept which comes, this is the central idea, that is called what is geodesic incompleteness. Now, before understanding incompleteness, we should understand completeness. So in space-time, geodesically is geodesically complete when we say that every maximal geodesic within it can be extended indefinitely in both directions. So it goes on and on and on and on and on. So that is what is called geodesically complete. So you see this is a future and past light cone, and this blue line, it is extending from the past into the right now and goes to the future light and goes on and on and on. So Minkowski space-time, flat space-time, this is also a model of flat space and geodesically complete. So any object can keep traveling eternally along a straight line. Okay, so from completeness, let us try to explain and understand what is incompleteness. So space-time is geodesically incomplete if there are at least one maximal geodesic that cannot be extended indefinitely. So there is one point where the geodesic is stopping. There's one point where the geodesic cannot be extended further. And this is the diagram, typically a kind of a black hole or anything, a strong gravitating mass where the geodesic, and remember the geodesics that we are talking about are what kind of geodesics? These are congruence of time-like geodesics as far as Raychaudhuri equation is concerned. So here you see any extended geodesic comes to a stop because it falls within the black hole and it converges. So that means it is called geodesically incomplete. And this actually leads to us to this point where we say that this geodesic incompleteness actually leads to few important points which we need to mention. First is that points where space-time curvature becomes infinite and geodesics simply end there. These are called timelike singularities. So timelike singularities on the other hand are often associated with the beginning or end of the universe where the laws of physics are breaking down. And another is that the space-time singularities. You can think that the fabric of space-time tear up has been torn apart due to the heavy mass, whatever. And the space-like singularities are typically caused by the collapse of the massive objects such as stars, which creates an intense gravitational fields. And there can be a third possibility, very hypothetical, but there can be a possibility which says boundaries. That means space-time might have defined edges beyond which geodesics cannot go. It will fall or whatever it will happen. Depends. So the boundaries also say that there is a geodesic incompleteness. Here this is important. We are talking of incompleteness, but technically we should say this. In general relativity, more than useful than geodesic completeness is geodesical maximality. So what do we mean by this term geodesical maximality? It tells you that every geodesic either goes to infinite values, that means geodesically complete, of affine parameter, or ends in a singularity. So we should not talk of geodesic completeness technically, we should talk of geodesical maximality. That means either goes to infinite of affine parameter or it ends in a singularity. So that is due to the fact that general relativity space-time can have singularities, so demanding geodesical completeness will be too restrictive. And here comes why it is important in Raychaudhuri equation. Singularity can be defined by geodesic incompleteness, and Raychaudhuri equation is the main key, is the key ingredient to define geodesic incompleteness, and we are coming to that part. So this completes our basic, I would say, foundation or the basic concept that we need to understand Raychaudhuri equation, and now we will understand how AKR or Professor Amalkumarraychaudhuri arrived at the Raychaudhuri equation. Now, after the foundation of Einstein's general theory of relativity, which this very equation, and I've made me several videos explaining Einstein field equation, he assumed three things. First, that the universe is homogeneous, that the universe is isotropic, and that the universe is static. However, that static condition was introduced by this lambda sign, and that was later removed by Einstein. But anyway, this was basically his assumption. Now, in 1922, Alexander Friedmann, another Polish mathematician and scientist, in line with a theory of relativity, introduced the idea that the universe is not static. Now, this is something very interesting. Most of us, quote the name of Edwin Hubble and the Hubble Space Telescope, how they measured that the galaxies are flying away. But it came in the year in 1929. But you see, Alexander Friedmann's model, a theoretical model, came in 1922. And this Friedmann equations, which I'm going to show you, are a set of equations in physical cosmology that govern the expansion of the space in homogeneous and isotropic model. So the static model is already gone. Even Friedmann is not assuming it to be a static, but he is assuming it is homogeneous and it is isotropic. Then came the famous Edwin Hubble and Mintel L. Humasson's prediction, and what they found is that around 1929, the systematic redshift actually showed us that the universe is expanding and the galaxies are receding from us, and Hubble's observation provided that the early insights into the origins of our universe. I mean to say, this is the background. We will come to AKR very soon. Now, we call this as Friedmann-Lemma-Robertson-Walker metric, because it is taken into account all those physicists, and this is an almost an exact solution of Einstein's field equation. The metric is this. I'm not going ahead to explain this metric, but it will take some time. So what it assumes is that yes, it is homogeneous, yes, it is isotropic, and it also assumes that this is an expanding universe. Now herein comes the problem where we find Professor AKR. The problem is that if we get a universe, this is the expanding universe, right? And we take the portion of the universe. So technically we should understand that AKR's theory would be something very central to what is called one part of the universe. He's not taking into account the entire universe. Okay. So what it does is that here you see the universe, it is expanding, and it is expanding, and it is expanding further. So it is continuously expanding. Now the question is that if it is expanding right now, then at some point of time it was contracting, and further contracting, and further contracting, and further contracting, and to certain other things. So with the Friedman-Lemma-Robertson-Walker metric, what we get, it is homogeneous, isotropic, and expanding universe. That is fine. But the question that AKR asked was that if it is expanding right now, then it was contracting, and contracting. And from here, what we say is that at one point of time, the universe was nothing but a single dot, right? And the universe was at a finite time reduced to a point. Now, this is very important. This word finite. It cannot be an infinite time. It will, if there is an infinite time, we would escape the singularity. I will show you how. So one is that the matter content of the universe was obviously infinite, and the other conditions, which was later introduced by Gamow, like temperature, etc., they would also become infinite. And physicists were not comfortable with this, obviously, because how can infinity and zero volume, all those things, that would create a lot of problem. And mathematicians, we do not like it because we cannot further go forward for that. Here comes this is the picture of Professor AKR. So what AKR told is that he won't take into account homogeneity and isotropy. Now you see that now you understand homogeneity and isotropy because I laid the foundation right at the beginning of the video. So what AKR told is that he found that if you give up homogeneity and isotropy, giving up homogeneity and isotropy would not help. It would include something which is called a rotation, and this might help us to avoid singularity or a Big Bang. So this is, this is how you see AKR is arriving at the equation. That if the matter content of the universe was infinite, other condition is zero or infinite or whatsoever, giving weird conditions, even if giving up homogeneity and isotropy was not enough, there has to be something which is called rotation. And this might help us to avoid singularity, Big Bang, and it might help us to create a better mathematical solution. So here what we see is that the question he asked in 1950 and the paper came around 1955. Number one is that, is the cosmological singularities generic? That means it is general in nature. And is there any non-singular solutions? When we mean non-singular means that can we avoid singularity? So here you see in both those figures, the trajectories of geodesics will focus at a point and cannot go past that point. It will focus at one single point, and that leads to geodesic incompleteness. Now you see all those foundations that we made are related to one to another and to another. So if we get a kind of a cosmological singularity, it is going to have a geodesic incompleteness which we are going to avoid. And can we find out that? That was the question, central question which AKR made around 1950, that how to escape singularity. Now in order to escape singularity, we have two solutions, and I will show you what are those. First is that the zero volume is reached at an infinite past. So if we get the zero volume or whatever the matter content or the stress energy momentum tensor, then if it is at infinite past, there is no problem. We don't deal with infinities anymore. And there was a minimum volume. If we get something which is a minimum volume, which is shrunk further, but has got a minimum volume, we can do the computations. But what our model, our theoretical calculation shows that it was at a finite past. That means there is no infinite past. And here comes AKR's brilliant, introspection. That giving up homogeneity and isotropy would not help. Only if we include rotation, then possibly we could escape Big Bang. And the equation, I will take this equation, right, for the timing. There's a reason for that. You see that there is a positive sign behind the omega squared, and this positive sign is the rotation. And what AKR told in this equation, that hopefully, and all other signs are negative, you see -4 and this second order differential, and then the sigma, that is the shear, etc. So what he told, that hopefully if we add rotation, because rotation has got a positive sign, we get a positive r double dot, that is the acceleration part, and it will possibly help us to save from singularity. This was actually the seminal contribution. This is how AKR arrived at the equation. And now we will speak of decoding the Raychaudhuri equation, or what actually the Raychaudhuri equation means and why it is so important, coming up in this part of the video. So when we take homogeneity and isotropy, we get this kind of equation. But what Raychaudhuri told is that what happened to the universe, or to a region of the universe, if we include these conditions. What are those? There can be a peculiarity of motion associated with a shear and a rotation. Now look into this kind of an equation. This has got a negative sign, and what does that mean? Acceleration. So the second derivative of r, which is typically the acceleration of the length which is with respect to time. Now because it is negative, if you go back in time and go back, that is contraction of the universe, you will obtain a zero value of r. That means the whole universe is going to contract at a point in a finite time. So this is a problem. That means we cannot avoid singularity. The second, I am sorry that I have ignored the sigma, the rho part, which is actually the density part. The shear also has got a negative sign. So shear, if it is negative, it would hasten up the gravitational collapse and helps the universe move more faster to achieve singularity. And there is a positive omega sign, that is a positive r. That means a positive rotation. So if the rotation is positive, and if you substitute the value, then possibly we can get a positive r double dot, and hence help the universe not go into singularity and thereby save ourselves. And that is I call saving us from gravitational collapse leading to singularity. So here comes his argument. So what AKR argued is that by simply avoiding homogeneity and isotropy, which brings in shear, won't be helpful. In order to avoid singularity, if we include rotation, hopefully we can avoid singularity. So the Raychaudhuri equation tells us that except under unusual circumstances, a singularity is inevitable in classical physics, at least as in general relativity. And the only way, once we get to the quantum theory of gravity, which is still we are trying to find, we might escape gravitational collapse, eventually leading to singularity. So the most important point is that at singularity, all physical laws break down. Second thing is that from a geometric point of view, singularity can be defined in terms of geometric incompleteness. We have seen that. Now the Raychaudhuri equation, which is an evolution equation for the expansion scalar, is an evolution, right? A family of time-like congruent geodesics. Right? So the Raychaudhuri equation, which is an evolution equation for the expansion scalar of a congruence of a time-like or null geodesic, is the main ingredient in the singularity theorem. We will look into that, why it is the main ingredient. And the Raychaudhuri equation, together with some condition on matter, proves the inevitable existence of singularity in Einstein's gravity. Now when we talk that if you include, that means the Raychaudhuri equation is holding the main key of singularity theorems, which is leading to the collapse. And if you put a little bit of matter inside, which is this rho sign, it would prove that it is inevitable. It is doomed to go for singularity in Einstein's gravity. Now when we talk of inevitable existence of singularity, do we mean by that Einstein's general theory of relativity has got a limitation? Now here I come to Professor Parthasarathi Majumdar of Indian Institute of Cultivation of Science, and in an interview made a wonderful remark. And he told that Einstein's theory has a fundamental limitation. He also commented that at some point you have to go beyond Einstein's theory, because Raychaudhuri equation establishes a key way to analyze and understand spacetime singularities. Indeed, because what will happen, when it will happen, can we include rotation? So it establishes a key way to understand spacetime singularities. And he also produced a kind of a little bit frustration, which I also feel, that AKR's recognition came much later given to this seminal and fundamental work in fundamental in physics. Now this, it left it in a very tantalizing way that there is a shear which is helping gravitational collapse, and there's a rotation which is preventing, and that led to lot of big scientists during the early 1960s to take up this equation and further create certain equations, and among them is Roger Penrose and Stephen Hawking. And Raychaudhuri equation is one of the key of Penrose Hawking theorem. How and where it is, let us into the next part of the video. The first thing is that I would like to quote, this is almost an unreadable book, at least for me, my mathematical limitation, The Large Scale Structure of Space-Time by Stephen Hawking and George F.R. Ellis. And I would like to show you that in this book, how many times Stephen Hawking has quoted Raychaudhuri. The first is this. You see, he clearly writes that in so and so we derive the formula for the rate of change of vorticity, shear and expansion. The equation of the rate of change of expansion, which is called the Raychaudhuri equation, plays a central role in the proofs of the singularity theorems, and so and so. So in chapter number 4, Professor Hawking first quotes that the rate of change of vorticity, which is the rotation. Shear, we have seen expansion of such families of curves. We have also seen what those families of curves. The equation of what the rate of changing plays a central role for the proofs of singularity theorem. Also, you see here, he writes that equation so and so is the analog of the Raychaudhuri equation for timelike geodesics. One sees again that vorticity, that is the rotation, causes expansion, while shear causes contraction. What a great moment for all the AKR lovers who can see this video right on my channel, is that Stephen Hawking himself is quoting, and I've underlined that because I've got those books. And not only that, how many occasions has Hawking quoted Raychaudhuri? 1, 2, 3, 4, 5. No, I'm not teaching you counting, but I'm just showing you these are from the pages that immensely he has shown the Raychaudhuri equation and Raychaudhuri equation and Raychaudhuri equation. I mean to say there are other references also, but for the sake of the video. So it shows how George R. F. Ellis and Stephen Hawking in their book has quoted what is called the singularity theorem. Now the Penrose Hawking theorem, what Roger Penrose, I will say the Penrose singularity theorem, what does it says? That if a space-time contains in a trapped surface, I will show you what is a trapped surface, from a region light ray can, no outgoing light ray, that means they cannot escape, then the space-time must contain a geodesically incomplete region, which typically includes the singularity, and this is what is called a trapped surface, right? So this is happening to be a singularity. So this was Roger Penrose in 1965, what is called the Penrose singularity theorem. Later, Stephen Hawking also made it in his own singularity theorem. And you see, Roger Penrose theorem was applicable only to black holes, while Hawking's singularity theorem was applicable to the entire universe. So walk back in time, and it says that if our current understanding is good, then there must be have been a singularity in the past. And they also includes the trapped surface. So the theorem is actually built upon Penrose's work only, and it states that universe expands in the past and satisfies the null energy condition, then there must be a past singularity where the curvature of space-time diverges. This implies a beginning, often interpreted as Big Bang. Now, these are 65 and 70, so you can see both of them more or less coming at the same time. Now, you see here the together that is called the Penrose-Hawking theorem, unified version, and it has got a very much good relation to Raychaudhuri equation. And why it is so? The reason is that these theorems rely heavily on the Raychaudhuri equation. I will show you that they have used it as a tool which describes what? 1, expansion, number shear, number 2, shear, and rotation of matter in space-time. So what the Penrose-Hawking theorem proved, that by analyzing the behavior of these terms based on theorem's assumption, the theorems demonstrate the inevitable divergence of the curvatures at some point in future past, leading to a singularity. So this is basically the relation, and not only that, I am going to show you. So this is one of the papers with Jose M. Senovilla, and David Garfinkel cited in the famous Penrose Hawking theorem. And here you can see that how many places this Raychaudhuriequation has been cited. So this is a kind of a proof. I've just taken screenshots. If you want to read any of those papers, I'm putting all the paper description link in the description box. So for the Penrose theorem, the expansion term in the equation indicates the trapped surface. For Hawking's theorem, focusing effect of light rays using the Raychaudhuri equation showed that they must converge to a point implying a singularity. And the relation is that the Penrose Hawking singularity theorems, they utilize the Raychaudhuri equations. If you read those papers, you will understand, as a key tool. Again, I repeat, they utilize the Raychaudhuri equation as a key tool to analyze the evolution of space-time and identify where our current understanding breaks down. While their implications are very much profound, these theorems also highlight that we need to further explore gravity and space-time in the singularities at the singularities realm. Now, this actually shows what is Penrose Hawking's theorem and how it has got. So the underpinning force is the Raychaudhuri equation. I hope you got it by this point. So that's it. And now a few important points which I have missed in this video. I would say I won't say missed, but it carries a lot of scope. So if I take the Raychaudhuri equation, this and this, the first and the second, then first it is called Raychaudhuri equations, not a equation. Now, why it is not called an equation, not equation? That means there are many equations. Yes, it is. I'm going to show you in the next part of the video. So the shear has got a set of equations and the rotation also has a set of equations. Point number 2 is that the Raychaudhuri equations are broader in scope and generality. By that, what I mean is that the Raychaudhuri equations will exist even if there is no theory of gravity. And most importantly, wherever there will be a vector field, wherever there will be a flow, there will be a Raychaudhuri equation. That was one of the greatest contribution from the Indian scientist, and I'm just paying my tribute to this great personality, Professor Amalkumarraychaudhuri. So you see, it is not limited to general relativity, it is not limited even to gravity. Wherever there will be a vector, I'm going to show you a little bit mathematically. If you want, please do comment on that. This video would not have been fulfilled by a note of thanks to few of the professors. Professor Soumitra Sengupta, obviously a fatherly figure who came to my podcast, and I think I can request him again to come on that. This paper of Shayan Kaur and Professor Soumitra Sengupta, the link is there, and he has been directing and guiding me throughout. So a note of thanks to Professor Sengupta very much on that. The second is Professor Narayan Banerjee from IISER, Kolkata, and I have cited many times from this lecture of Dr. Narayan Banerjee, and I will give you a big surprise. I'm not announcing it right now on this video. Immense thanks to Dr. Narayan Banerjee, Professor Banerjee from IISER, Kolkata, and you can see this video. I also put it in the link. The next is through my email correspondence with the great Professor Shayan Kaur and his video or lecture on Raychaudhuri effect, which was at IISER, Kolkata at IIT. He is a professor of physics, very celebrated, very dignified professor, very respectable professor from IIT Kharagpur. So without these three and many others, those which I have cited, I'm putting it up in the links. And I really thank you for taking up your time for watching this video on Raychaudhuri equation. If you have liked, please do subscribe and click on the bell icon to get all the notification from Physics for Students. If you have any query, please do write to me at this email ID. Don't forget to subscribe to my other channel where I put videos exclusive to General Theory of Relativity, and you can follow me on my Facebook, Instagram, LinkedIn and Twitter account. So that's all for the AKR part 1, I would say, and I will make further videos on the second part depending upon the comment, your like, and Physics for Students will be soon back with a lot of more surprises coming up. Till then, goodbye.